Alright class, I'm going to go over with you how to do number 3 here. So we will look at this problem and we see that we're going back to exercise 1, but it's just a coin toss exercise. And in this one, the students are tossing the coin 25 times each. Use the 68, 95, 99.7 rule to describe the sampling distribution model. So when we are making our distributions, we're looking for a couple values first. First, we need the p-value here, the probability that it's going to come up heads, which we know is just going to be 0.5 or 50%, right? Because if you flip a coin, you have a 50% chance of being heads. The next number we need is that standard deviation, right, which is a different calculation. So to find that, we use our p-value times 1 minus our p-value all over the number of values in our sample. And then we take the square root of that. So here I've gone ahead and filled in the numbers we have for this problem. So we have 0.5 being our p-value times 1 minus 0.5. It's not always going to be this easy. This is just because we have that 50%. But there we have that divided by 25, which is our number of times each person is flipping the coin. And that comes out to be a 0.1. And that is our standard deviation here. So if we remember our 68, 95, 99.7 rule, our 68% of our data is going to fall between one standard deviation below and above the mean. So here we have 60% of our data is going to be between 0.4 and 0.6. 95% of our data will be between two standard deviations above or below. Therefore, we see that 95% of this data will be between 0.3 and 0.7. And for the last one here, we round out with 3 standard deviations above and below gives us 99.7% of the data, falling within the range of 0.6 to 0.8. All right, here on part B, we see that we need to confirm that we even can use the normal model here. And so to determine here, we need to determine whether or not we meet the 10 failures, 10 successes rule, correct? So what we need to do first is we start out by multiplying the number of samples, number of values within our sample set, times our probability, and that has to be greater than 10. We also need the failure side. So we need that same number of samples, number of values in the samples, multiplied by 1 minus the probability, and that has to be greater than 10 as well. So here to fill in the numbers, we have 25 times 0.5. It's going to be the same since both the values are the same. We see that it's 12.5, which is indeed bigger than 10. Alrighty, now for part C, we see that they're increasing the number of tosses to 64 each. So we're going to make a new distribution model here and label it appropriately and show you all of that. Alright, so we're going to start off similar to what we did on problem A, on part A. So we start here. We know that the same is going to be 0.5. We're tossing coins again, so we know there's a 50% chance of getting heads. So the top part's going to be the same up here, but what we're changing here is this n value that we put in the denominator, which is going to shrink our standard deviation down to 0.0625. So here, if we come down here, draw it out, we see that now 68% of our data falls between 0.4375 and 0.5625. We see that 95% of our data falls between 0.375 and 0.625. 99.7% of our data goes between 0.3125 and 0.6875. Now we need to check and see that the normal model here is appropriate. So we did the same thing we did on the last one, and we multiply n times the probability that we'll get heads, which is 64 times 0.5 equals 32. And again, we see that this is greater than 10. So again, the normal model will work in this instance. Alright, so we know the normal model works, and this is going to be your distribution setup. So you need to write this answer down. N is equal to 0.5 and 0.625. Alright, and now for part D, we need to explain how the sampling distribution model changes as the number of tosses increases. So here I've redrawn out the two curves. This one being with 25 tosses, this one here being, this one here being with 64 tosses, this one here being with the 25 original tosses. And we see here that because of the standard deviation being larger down here, that 68% falls into a larger range from 0.4 to 0.6, whereas in this one up here with the 64 tosses, your standard deviations are smaller. So 68% of this data falls into a much smaller range here, and that causes the model to be thinner and taller. So what you can take from this is that the larger the n is, the thinner and taller your standard model is going to be, your normal model. So for problem number 5 here, we have one student who tossed her coin 200 times and found that only 40% of the time it was heads. This sounds like a number that's a little lower than what we expect, considering we would expect 50% of the time to have heads. So basically what this question is asking is, do we think this student is full of baloney? And now we're going to prove that mathematically, whether we believe it or not. Alright, so first thing I'm going to do here is draw out my distribution here, and to do that we know the p-value is going to be 0.5, right, because we're still dealing with coin tosses. So we have our top line here is no different for our standard deviation. The bottom line here is going to be 200 though, since our sample size was 200. If you do this math here, it gives you a standard deviation of 0.0354. So then I went down here and drew my curve. This right here is our mean at 0.5, our p-value. And so we need, right here, we need to find our 0.42 and what the probability is that it will fall on this line or to the left here. So what we can do here is go to our normal CDF, use our negative infinity lower boundary, 0.42 upper boundary, 0.5, 0.03454. And what that gives us is that there is about a 1.2% chance of this happening. So I would say that is not impossible, however, it is somewhat unlikely. Another way you can look at this is by looking at the z-scores. So if you want to know how many z-scores away from the 0.5 that we expect this number is, we take our expected value, our p-value, right here, of 0.5, and we subtract from that. We take our actual value away from there, our actual p-value, or p-hat, and then we divide that by, and that should be a 0 right there, but 0.0354. And what we find is that gives us 2.26 z-scores away. And if you remember back to earlier when we talked about z-scores, we know that anything above 2 is a strange z-score, but anything below, we're looking for above 3 z-scores above the mean to be anything that is extraordinary or just out of the realm of possibility. So again, I would land on this student as it's definitely possible this should have happened, probably unlikely though.